notes. This is example actually which I once met in one of my research papers. So I'll open the determinant. It's a big one. I'll give you some time to copy that. I'll explain the structure of it. So it's a determinant of size n plus 1, you see? That's my matrix. I will call it J sub n of A. So it's a matrix of size n plus 1, And that's the one which has, look at this, what was the structure of the matrix. You have this A in the first entry, then the rest of the first row is negative y's, all of these parameters just numbers. And you have another set of parameters here, S1, S2, Sn, take 1, Sn. Actually, you also have the y's on the diagonal. The rest of the matrix filled with zeros. Just for your convenience, in fact, I put here the version of this matrix when size is 4, just to give you more understanding what the structure of it is. So you see, you got S parameters in the first column, beside the first element. You got negative y's here, and you got y's across the diagonal, the rest filled with zeros. Some of you who will continue studying math in the second year, you will find actual determinants. I mean, so far we just discussed the determinants in the pure algebraic context, system of linear equations, row echelon forms. There will be some other algebraic context maybe later. You will actually, when you study your second year, you will realize actually determinants has a very natural context in geometry and analysis, especially when it comes to like deforming the n-dimensional space. So for instance, if you start bending your space in some peculiar way, the way the volume of the space will change, that's where the determinants appears. In fact, you will find this in the subject which is called substitution in multiple integrals. And actually that's how I came across the determinant. We were looking at some integral, and we needed to make some transformations to that, and the formal process involved determinants, and that's how the determinant appeared. We spent it's not really difficult to compute that, probably half an hour, and we just find the way how to find the value for this determinant analytically. And it's basically a row decomposition. Look what we're going to do. So in fact, for the sake of that task I was doing back, it was 3 or 4 months ago, we were looking at this we were looking at the number D, which is this determinant with this value A specifically chosen like this. So it's actually this A connected with these parameters. It's just I separated this because if I put this long number in here, my matrix will start looking ugly. That's why I just put it down here. So I think what we did there. So when we went after this, we used the column decomposition. We did the way we did the column decompositions with you a few times already, and we used this last column for this column decomposition. So look what will happen if I use this last column. First, look at this case. When I look at this number, y at the bottom, the remaining bit, that's the minor. Sorry, that's the remaining minor. That's the remaining minor. It's the minor of n take 1 take 1 size, so it will be the minor of size n times n, right? The original was n plus 1, n plus 1. And if you look closely at this minor, you will realize that this minor is in fact, if you look closely at this minor, you will realize this minor is in fact the same structured matrix, similarly structured matrix like this, but one size smaller. Do you see that? So this sort of column decomposition give me this first term, element y, times the minor, that's the minor, of size n take 1, of size n actually, but the index will be here, n take 1. The more interesting part will happen when all of these zeros, they all will be zeros. Nothing interesting comes from here, but something interesting comes from here when I look at this element. Look what happens when I look at this element. This is a position sign. Remember, we alternate the signs. So here I have to put the sign, I have to add the row index, and I have to add the column index. The row index here 1, the column index here n plus 1, that's why here n plus 2. Then goes the element itself, negative y, and then will come the minor. Let's just see what I put for minor. Oh, I put the whole thing. Okay, I'll explain this in a second. So again, I'll just take you through all of this thing which appeared here. This one is a position sign for this element. Remember, the position sign is sum of the row and the column index. This one, the element itself. These two, look what happened with these two. These two, actually, I was looking at the minor already, this whole minor. And for this minor, I think for this whole minor, we use the row decomposition with this row, this one and this one. No, it's all right. No. Actually, I use the first column. Look at this. For the smaller minor, I'm not going to copy this again. I use the first column for the decomposition. Look what happens with these elements. When I use the first column, I have to take this element, right? Cross out the row, cross out the column, and multiply with even a smaller minor. But the interesting thing about the smaller minor, it has the 0 row. So this smaller minor is 0 in fact. Do you see that? That's the key thing here. So if I go with this S1 and multiply by the minor, I can of course copy that. But this minor will be just 0 because we have 0 row. So when I take this other cross down, no, it's the wrong cross. Can I reach this cross? Yes. If I take it here, the same story happens. We have 0 row, so this minor will also. So you see, this time the whole thing vanishes not because we have 0 elements in the column, but we have actually minus which have 0 row in it. So this will be 0. All of this will be 0, including this before the last one. The only one which will have non-zero minor is the very last one, Sn, because this time we cross out the 0 row. So for this minor, I put here the position sign for this Sn. The position sign here, this one. We have to add the row index here and the row index here, n, because now its size is small, and the column index is 1. Then we multiply the element again. And look what's left here. What is left is this little box, this little minor here. This little minor is triangular shaped. So this little minor is just a product of the elements on the diagonal. And the elements on the diagonal, it's just letter y, repeated how many times? And take 1 times. And that's the finish of the whole explanation. So we're doing this rather sophisticated row decomposition. We just come up with this recursive relation between the minor of size n and the minor of size n take 1. Now we can unravel this down to the size 0 and see what the formula will give us. So I did this unraveling here. Look at this. So if I open these brackets, if I just take care of all of these signs and everything, actually it will look like this, as simple as this. Because this -1 square is just nothing. N plus n is double n, which is again square, so negative is gone. 1 extra negative here will cancel this negative. So that's the expression for that. If I start substituting, if I start doing my recursive relation, if I replace this j n take 1 with a similar relation in terms of the j n take 2, that's how it will look. Right? I just replaced this. I just wrote similar identity like this, but for the n take 1. So this j n take 1 gets replaced with this brackets. If you expand everything here, make it look simpler, it will be y square, right? Y square times j n take 1. Here will be something like this, right? This y times this y n take 1, it's s n take 1, and it's a common factor. I put it like this. You can just keep repeating. You can repeat this substitution of this j with the recursive relation further. But you can probably see the pattern already here. The pattern here is just like we add up the s elements here. Well, I see and here you just the power of this y combined with this index together is n. So if you do it all the way to the 0 level, you will end up with this. So if you now sub in, because J naught, it's a matrix with just one element like this. If you just look at the structure here, J naught matrix, so it's a matrix of size 1 times 1, it's just a number. And that will be just the number A. And the number A here is this number, 1 take S1 take Sn. So if you sub in this number, the whole G will be just y to the power n. This number G we were after 4 months ago is just y to the power n.